Have you ever wondered how oil and water interact, or why certain substances mix while others don't? Welcome to the intriguing world of disperse systems, where the rules of chemistry and physics intertwine to create fascinating phenomena. A disperse system is a form of matter dispersion that occurs when one substance is spread or dispersed in another. Think of a misty morning, where tiny droplets of water are dispersed in the air, creating a fog. Or consider the tiny particles of cocoa suspended in hot water to create your favorite hot chocolate. These are examples of disperse systems, and they are more common in our daily life than you might think. From the food we eat to the medicines we take, disperse systems play a crucial role. In the food industry, for instance, emulsions like mayonnaise or butter are examples of disperse systems where tiny droplets of one liquid are scattered in another. Similarly, in pharmaceuticals, disperse systems like suspensions or aerosols are used to deliver drugs effectively to our bodies. But disperse systems are not just limited to these industries, they are prevalent in nature too. The blue hue of the sky, that's Rayleigh scattering, a type of disperse system where tiny molecules of air scatter short wavelength light, such blue and violet light, to the four corners of the sky. Understanding disperse systems can also lead to the development of new materials and technologies. For instance, the science of disperse systems is being used to create new types of smart materials that can change their properties in response to changes in their environment. But how do these disperse systems work? What governs the interaction between the dispersed particles and the medium in which they are dispersed? Here's where we need to delve a little deeper and understand the concept of free energy in these systems. Now that we understand what dispersed systems are, let's explore the concept of free energy consideration in these systems. So, what exactly determines the stability of these dispersed systems? Well, it all boils down to the free energy of the system. You see, in the realm of dispersed systems, the stability of these systems is intricately tied to their free energy. This is a measure of the total energy of a system that is available to perform work at a constant temperature and pressure. Now, you might be wondering, why is free energy so important? The answer lies in the fact that systems inherently tend to minimize their free energy. This principle, known as the principle of minimum energy, is a fundamental law of nature. It's the universe's way of saying, hey, let's take the path of least resistance. But here's where it gets interesting. Free energy is not just about the energy available for work. It's also about the balance between two key factors, entropy and enthalpy. In simple terms, entropy is the measure of disorder in a system, while enthalpy represents the total energy of a system. In the context of dispersed systems, an increase in entropy or disorder tends to stabilize the system. This is because more disordered states have more ways of arranging themselves, and nature, being the efficient entity that it is, loves options. On the other hand, changes in enthalpy can either stabilize or destabilize a system. If a process leads to a decrease in the system's enthalpy, it's generally stabilizing. But if it increases the enthalpy, it can destabilize the system. So, to wrap it up, the stability of a dispersed system is determined by its free energy, which is a delicate balance between entropy and enthalpy. The system will naturally shift towards states that minimize its free energy, favoring increased entropy and decreased enthalpy. Now that we have a grasp on free energy consideration, let's delve deeper into the different types of stability in dispersed systems. Did you know there are two types of stability that govern dispersed systems? Let's delve into this a little deeper. Picture a tightrope walker high above a cityscape. The walker's goal is to maintain balance and prevent a fall. This delicate balance is akin to the thermodynamic stability in dispersed systems. The system strives to achieve the lowest free energy state, making it more stable. It's like our tightrope walker, who is most stable when perfectly balanced on the rope. However, what happens if a gust of wind blows? The walker may sway but doesn't necessarily fall. This introduces us to kinetic stability. Kinetic stability is all about the rate of change, or how fast the system can move from one state to another. In the tightrope walker scenario, the gust of wind represents a disturbance to the system. Even though the walker sways, they don't immediately fall. the rate at which they can recover and regain balance represents kinetic stability. In the realm of dispersed systems, thermodynamic stability is governed by the system's free energy. The system will naturally gravitate towards the state of lowest free energy, just like water flowing downhill. On the other hand, kinetic stability is about how quickly a system can change. It's about the speed of the reaction or how fast a system can move from one state to another. So, in a nutshell, thermodynamic stability is like the ultimate goal, the state of perfect balance. But kinetic stability? That's the journey, the ups and downs, the swaying of the tightrope walker in the wind. It's about how fast or slow we get to that state of balance. Both types of stability play crucial roles in understanding and predicting the behavior of dispersed systems. They provide a framework for us to understand how these systems react under different conditions and how we can manipulate them for our benefit. With that understanding of thermodynamic and kinetic stability, let's move on to the DLVO theory. Have you ever wondered how particles in a dispersed system interact with each other? Well, the answer lies in a theory called the DLVO theory. Named after Derjaguin, Landau, Verwey, and Overbeek, the pioneers who contributed to its formulation, DLVO theory aims to describe the intricate interactions between charged particles immersed in a liquid. So, let's delve deeper. The DLVO theory is primarily based on two fundamental forces. The first one is the van der Waals attraction, a ubiquitous force that draws particles together regardless of their charge. Originating from quantum mechanical effects, it results from temporary fluctuations in the electron distribution around atoms, leading to instantaneous dipoles that induce opposite dipoles in nearby particles. The second force is the electrostatic repulsion, which comes into play when the particles carry the same charge. Like charges repel each other, and this repulsion prevents the particles from coming too close, effectively opposing the van der Waals attraction. The interplay between these two forces, the attractive van der Waals forces and the repulsive electrostatic forces, governs the behavior of particles in a dispersed system. When the particles are far apart, the van der Waals attraction dominates, but as they get closer, the electrostatic repulsion becomes stronger, creating an energy barrier that prevents the particles from clumping together spontaneously. The beauty of the DLVO theory is that it provides a quantitative understanding of this delicate balance. It allows us to predict the stability of a dispersed system, helping us manipulate the system for various applications, from industrial processes to cutting-edge research in nanotechnology and medicine. Remember, the DLVO theory isn't just an abstract concept. It's a practical tool that helps us understand and control the world at the microscopic level. Knowledge of these interactions is vital in various fields of science and technology, from designing new materials to understanding biological systems. Now let's classify dispersed systems. Did you know that dispersed systems can be classified based on various factors? Indeed, the world of dispersed systems is far from monotonous. It's a vibrant landscape of diversity, where systems are classified based on the size of the dispersed particles, the nature of the dispersion medium, and the interaction between the dispersed phase and the dispersion medium. Let's explore each one in detail. First, we look at the size of the dispersed particles. Here, we have three main categories. Colloidal systems are characterized by particle sizes between 1 and 1,000 nanometers. If the size exceeds 1,000 nanometers, we're dealing with coarse dispersions or suspensions. Then we have true solutions, where the particle size is less than 1 nanometer. Next, we consider the nature of the dispersion medium. This classification gives us the familiar terms we often encounter: aerosols, foams, emulsions, and so on. Aerosols, for example, are systems where solid or liquid particles are dispersed in a gas. Foams, on the other hand, are gas particles dispersed in a liquid or solid. Emulsions, these are liquid particles dispersed in another liquid. Finally, we come to the interaction between the dispersed phase and the dispersion medium. This interaction determines the stability of the system. If the particles of the dispersed phase have an affinity for the dispersion medium, we have a lyophilic system. But if the particles are repelled by the dispersion medium, we have a lyophobic system. So, there you have it. Dispersed systems, far from being a uniform expanse, are a fascinating realm of diversity, shaped by the size of the dispersed particles, the nature of the dispersion medium, and the interaction between the two. With this, we have a good understanding of dispersed systems and their stability. Today, we have taken a deep dive into the fascinating world of dispersed systems. We've unraveled the mysteries of free energy consideration, contrasted thermodynamic and kinetic stability, and explored the intricacies of DLVO theory. The diverse classifications of dispersed systems have also been laid bare. This knowledge is a stepping stone to deeper understanding and further research. So if you're intrigued by the complexities of dispersed systems and thirst for more, don't forget to hit the subscribe button. Subscribe for more, because you won't find me later.